Hello, thank you for your interest in this presentation. My name is Fernando Resende. I am with the University of Texas at Tyler, and I am presenting today on behalf of Jiawing Li from Southeast University. He's the student that worked on this project. This is a work about fast pyrolysis of rice husk using a new hierarchical catalyst. And it was a project developed in collaboration Southeast University, the University of Washington, and the University of Texas at Tyler. So first, let's start talking about the feedstock of interest here. Rice husk, and the rice itself is the third most produced agricultural commodity in the world, with rice husk then being usually discarded just as an agricultural waste. It is a material with very small bulk density, and because of that, it is expensive to transport any amount of mass. And it also has a low energy content, only 16.2 megajoules per kilogram. So there is interest in upgrading this material, transforming it into more energy dense forms. The way we're going to do that is via fast pyrolysis. And fast pyrolysis is a thermal conversion over an inert atmosphere at high temperature, usually 500 to 600 degrees Celsius, and with very high heating rates and short residence times. Now, usually in fast pyrolysis, you're going to have three phases. There is a gas, a liquid pyrolysis oil, and char. The focus here on this work will be on the production of the liquid oil or bio oil. For essentially, we want to make liquid transportation fuels. Now, the issue here is that the bio oil from pyrolysis has characteristics that prevent it from being used as a transportation fuel. It has several hundred, essentially, organic oxygenated compounds, and those have reactive functional groups like aldehydes and ketones that provide poor chemical stability to the oil. It also has high viscosity, is not miscible with crude oil. It still has a low energy content. It's acidic and has a high water content. So if you see here the Van Kremlin diagram, the hydrogen to carbon ratio as a function of the oxygen carbon ratio shows that the bio oil has a very high oxygen content compared to more traditional fuels. So the way we're going to address this is by carrying out catalytic fast pyrolysis. So pyrolysis in the presence of a catalyst, which consists of deoxygenation over zeolites. And this can be done usually in two forms. The first one is in situ with the catalyst and the biomass mixed in a single unit. And the second one is ex situ with the biomass and the catalyst in separate units. Now here we're going to be focusing only on the in situ method with the biomass and the catalyst mixed, and microwave pyrolysis will be used as the method for heating this mixture. Now the catalyst here of interest is HZSM-5, which is a microporous molecular sieve, which is a pretty standard catalyst for catalytic fast pyrolysis. Now, what happens is that the strong acidity of the HZSM-5 helps promote the formation of aromatic hydrocarbons. However, the very small pore sizes of the HZSM-5, they are about the same size of some of the molecules involved here in this thermal processes, meaning that there are problems with plugging of micropores, coking, and thereby deactivation of the catalyst because of the coke. In contrast, here we have MCM-41 as another zeolite that sometimes is used for this process. MCM-41 is a mesoporous molecular sieve which has, because of much larger pore sizes, diameters, it doesn't face the same issues that HZSM-5 does in terms of plugging and coking. However, the MCM-41 has much strong, it doesn't have the same strength of the acid sites, it's much lower strength compared to HZSM-5, and is therefore not as active for the production of aromatic hydrocarbons. So the idea here, what we want to do is combine these two catalysts, use the HZSM-5 as a core and the MCM-41 as a shell, so that we can combine the positive characteristics of both to improve the catalytic fast pyrolysis process. Now, in addition to combining these two zeolite structures, what we decided to do here was to carry out modification of the actual microporous structure of the HZSM-5. So you see here a typical HZSM-5, it has acidic sites, usually strong acidic sites on the outer surface and weaker acid sites at the inside of the pore. So you see the space here, the pores with a small amount of mesopore. So that's a typical structure for the HZSM-5. There's a number of potential modifications that can be done with the catalyst, including adding metal. The one modification that we're going to be looking at here today is alkali treatment, essentially adding additional mesopores and also increasing the volume, the width of the existing mesopores. And the hypothesis here is that by doing so, we should minimize the issues with coking on the HZSM-5. Now, there are two types of alkali treatment here that could be used. The most used one is sodium hydroxide, the inorganic alkali treatment. That's a very severe treatment that tends to remove both strong and weak acid sites from the structure of the HZSM-5. What we're going to be trying here is tetrapropyl ammonium hydroxide, or TPAOH, which provides a different type of alkaline treatment, and it's a much more moderate treatment that continues to remove, it also removes the outer acidic sites from, strong acidic sites from the HZSM-5, but it tends to keep the weaker sites that are in the inner pores of the HZSM-5. So a more moderate treatment here is what we are applying for this specific work, with the hypothesis that it could help essentially keep the structure of the HZSM-5, avoiding a more severe treatment and therefore promoting the catalytic activity. So objectives, we're going to be evaluating some of the catalysis synthesis parameters on the topography and structure, and the process, we're going to be looking at how the temperature affects the product distribution, and in addition to that, compare our new hierarchical HZSM-5 MCM-41 catalyst with the pristine MCM-41 and HZSM-5. So here we have our results, XRD patterns for the HZSM-5, shown here in red, and in addition to have the HM here is denoting the hierarchical catalyst, so HZSM-5 MCM-41 with the TPAOH treatment. The numbers shown here are actually the molar concentration of TPAOH used in this treatment. That's what's varying in the graphs shown here. And what we observed is that the structure, the peak, the characteristic peaks for the HZSM-5 here from 7 to 9 degrees and from 22.5 to 25 degrees, those peaks remain unchanged at least until a concentration of 2 moles per liter of TPAOH, above which the intensity of the peaks decrease, indicating some severe destruction of the structure of the HZSM-5. On the right side here, what we see is the CTAB mass fraction. CTAB is simply the precursor for the formation of the shell, the MCM-41. And we have the pristine HZSM-5 here with increasing mass fractions of CTAB. There is not much of an effect on the structure here of the HZSM-5, with the exception of the higher concentrations for which you see a decrease in the size of the peaks, which is essentially related just to a smaller fraction of the HZSM-5 in the produced catalyst. TEM results, the images here just essentially just show illustrating for us the HZSM-5 is produced as the core with a layer of MCM-41 as the outer shell. So this was produced at a concentration of 2 mol per liters of TPAOH, a mass fraction of CTAB of 10%, digestion and crystallization temperatures of 110 degrees and 24 hours period each. Now for the actual catalyst characterization here in terms of the nitrogen adsorption and desorption isotherms, the HZSM-5 is shown here in red, and what we see, the other curves are the hierarchical catalysts with varying concentrations of TPAOH from 1 to 3 mol per liters. And what we observe is a stepwise increase in the volume adsorbed, with some hysteresis here for most of the HM, the newly produced catalyst, which indicates a type 4 isotherm, which suggests in turn that those catalysts have some mesoporous structures associated with them, which behavior which we do not observe with the pristine HZSM-5. So the nitrogen absorption curves, they suggest, or they are consistent with the idea that mesopores are being introduced because of the TPAOH treatment. Some structural parameters here, again, we have the pristine HZSM-5 and increasing concentrations of TPAOH. What I'd like to highlight here is the constant increase in the pore volumes and increase also in the pore width that is observed as we increase the concentration of TPAOH. After concentration higher than 2 moles per liter of TPAOH, however, the surface area starts to decrease, indicating some excessive destruction of the HZSM-5 structure. So now let's move on to talk about the results of the pyrolysis. And the first thing that we want to do here is look at how the temperature affects the results when we use this hierarchical catalyst. And here we have the yields of liquid, gas, and solid as a function of temperature. And what we observe at 550 degrees Celsius, where we obtain a maximum in terms of the liquid products. So we selected this temperature as we move forward and compare this catalyst with other ones. In terms of product distribution, we have a large amount of hydrocarbons here formed with the HM, the new catalyst, and the higher relative content, 60.5% obtained for a temperature of 550 degrees. As you see here, is a high selectivity for BTX, benzene, benzene, xylene, toluene. Now let's move on to talk about a comparison of the newly produced catalyst with the pristine MCM-41 and the HZSM-5. What we observe is that the newly produced catalyst here, the hierarchical catalyst, produces the highest amount of liquid, which is what we intend, right? And the MCM-41, the highest yield of gas, and the HZSM-5, the highest yield of solid, which is exactly what we expect based on the micropores, the size of the pores for the HZSM-5. When we compare the product distribution, we observe that the hierarchical catalyst has a much higher relative content here, defined as the peak area for hydrocarbons divided by the total peak area, 60.5%, which is much higher than, at about twice as much as what can be obtained with HZSM-5, and less than 5% that can be obtained with MCM-41. the selectivity very high here for toluene and xylene when we use this new catalyst. Now, the bottom line here, we wanted to compare the coke formation for this new catalyst with some other catalysts, and the coke yield here is reported for some of them. For the pristine HZSM-5 and no treatment, well, we produce 11.2% of coke. For another catalyst, essentially the same type of catalyst, HZSM-5, MCM-41, however, with sodium hydroxide, the inorganic alkali treatment, we were able to reduce the coke yield to 6.6%, but a more moderate treatment with TPAOH dropped down the yield of coke to only 4.7%. So the minimum coke among all of the catalysts that we use here was obtained with this new hierarchical catalyst with TPAOH organic treatment. So here, just finalizing the lump pathway that we are suggesting based on the results. The rice husk pyrolyzed, the thermal decomposition leads to macromolecular oxygenase, which then react on the shell MCM-41, reducing molecular size, producing smaller oxygenase, which then go into the modified HZSM-5, which has some mesopores because of the TPAOH treatment, generating mostly aromatics with some aliphatic hydrocarbons as well. So our conclusions here, the catalyst characterization suggests there is no damage on the crystal structure if we keep the TPAOH concentration under 2 moles per liter, and a moderate amount of mesopores is indicated by the nitrogen adsorption. All of this allows for an effective upgrade of the pyrolysis vapors producing hydrocarbons. The temperature here that provided the highest liquid yield was 550, 47.6% was the highest yield. The hydrocarbon content was maximum at 60.5% with the hierarchical catalyst, which is about twice as much as what can be obtained with MCM-41 and HZSM-5. So acknowledgements, so funding for this project from the National Natural Science Foundation of China, National Key Research Development Program of China, and the Scientific Research Foundation of the Graduate School of Southeast University. So that's it for today, and I'd like to thank you for your attention.